Hello, in this session we're talking about research design in physical geography. In particular we're talking about hypothesis testing, and I'm going to give you a particular very simple research case study that illustrates hypothesis testing in action. Now this is really important to you because physical geography is a research-based discipline. So in this first session I'm going to talk about research design and the hypothesis testing approach, and then in a follow-up session, in a follow-up video, I'm going to give you a case study about the origin of base lies. But the fact it's about base lies isn't the important thing. The important thing is that it's an example of hypothesis testing in action. Now this is really relevant to your degree studies because, as I say, physical geography is a research-based discipline, and research and your ability to do your own research and also to judge other people's research, to evaluate the research that you're reading about in the journals, that's a focal point of your undergraduate studies. Also involved in your undergraduate program, you have research training, you have field courses, you'll be doing projects, you'll be doing an independent study project or dissertation of your own, and many of you will carry on using the skills that you gain as part of this training in research design as part of your professional life afterwards also. So this first video, research design and the hypothesis testing approach. The next video, a case study of hypothesis testing in action. Now in terms of background reading for this, the first bit of background reading very obviously is a paper that we're going to use as a case study in the second video, and that's something that I wrote back in 1989. You can see there the stacking of basal debris layers without bulk freezing on isotopic evidence from West Greenland. That's from the Journal of Glaciology. I'll talk you through that paper in the context of the hypothesis that we were testing and how we tested it, and using it as an illustration of this approach to research, but you might want to just go and have a look at the paper afterwards yourself to follow up the details. And then the more general bit of reading that I recommend that you do associated with this session is chapter 6 in that book, How to Do Your Dissertation in Geography and Related Disciplines. It's a set text for some of the things that you'll be doing in second year as part of your degree. But if you read chapter 6 in that, it's about research design, and it picks up on some of the examples that we're using in this session. And both of those, they're in the reading list and they're available electronically online through the library or just on the internet. You should be able to get hold of those very easily. So make sure you do that background reading in association with what we're talking about in these videos. So to begin with, let's just think about the broad context of the stages that research in physical geography goes through, from having the first idea of something you want to find out, right the way through to getting a paper published and having your results out there impacting the research world, impacting the real world in terms of applied physical geography knowledge. So how does that work? What stages do we go through? Well, we begin with a broad context, and that might be to do with real-world problems or issues from the literature that give us questions. Why does this hillside keep collapsing? Where could we safely build something or other? What's the cause of this feature that we see in the landscape? What's the time scale over which these particular changes are going to happen in the landscape? There are all sorts of questions that arise from the broad context of our physical geography environment and the research that's been done previously on that environment, and that leads us to a question to which we're trying to get an answer or answers. And that's a typical starting point for research. And that's the background to where we now jump in and say, well, okay, you've got a question, you want to get an answer to it, or you've got a problem, you want to get a solution to it. How do you design a body of work, a program of activity, a research program to actually get that answer or to solve that problem? And that is research design, and that's a whole area that we're going to be talking about, a whole area in itself that we're going to be talking about in this session. Now typically once you've done your research design, you can then put in your research proposal or your proposal to get a grant if you're needing external funding. That grant proposal, that project proposal, then goes out for peer review. Now what that means, peer review, is review by other people like yourself. So if I put in a grant application, it will be reviewed by other scientists. If we had peer review at undergraduate at undergraduate level, what that would mean is that when you put in a proposal to do a dissertation project in your second or third year, if we had that project proposal reviewed by other undergraduates, that would be peer review. We don't actually do that at Keele. You'll have your proposal reviewed by a staff member. But peer review in the context of professional scientific research is a review of what you're planning to do by other people who have experience in doing that kind of work. That peer review will then lead to a decision about whether your project gets funded or not. If it doesn't get funded, then you're kind of back to the drawing board, and you can see on the diagram here, if you're not funded, well then you have to go back and think about it, come up with a better question, or more often come up with a more feasible research design. Typically the grant reviewers are likely to identify flaws in your research design that might say, well, if you do the research in that way, you're never going to get an answer to that question, or if you do the research in that way, your answer won't be a reliable answer. So you need to change how you do the research in order to get a reliable answer to your question. So you might go around in circles a little bit there until eventually you get the funding and you can go off and do the research. Doing the research, that's a whole separate set of stages in itself that we'll deal with elsewhere, but hopefully eventually, after carrying out your research, following the research design that you've set for yourself, you will then arrive at a conclusion to your particular research project, which might be an answer to your research question. But every answer that you arrive at in research inevitably just throws up more questions. We're never finished doing research. If we get the answer to the one question, well, that's going to raise a follow-up question, and that's going to give us another opportunity to study something a little bit more broadly, or a little bit more focused, or raise a project based on the first bit of work that actually leads into an even more important set of questions. Once you've got those conclusions and identified your next set of questions, then you go ahead and you write your paper, you submit that for publication. There's another round of peer review where people might say, no, your paper isn't clear enough, or no, your paper doesn't explain sufficiently well why you arrived at that conclusion based on those observations. You might even at that late stage get people writing reviews of your paper saying, well, this paper's no good because the research design was no good. Their results are flawed because their premises were flawed and the methods they used weren't appropriate to the questions that they were asking. This was a bad research design. It should never have been given funding to go ahead in the first place. So you're beginning to see research design is really important here. If you get a bad research design, you're not going to get an answer to your question anyway. You probably won't get funded. You probably won't get your papers accepted for publication. Your results are going to be rubbish, and you're not going to get down to that bottom line there, that having published the results of your work in the ideal world, that makes an impact, it makes a difference. There are responses to your work from other researchers who can pick it up and run with it and do new things. There are solutions to problems that can be applied to the real world. We've generated new knowledge. Now, I've said new provisional knowledge there, and I'm just going to leave that hanging, because by the end of this session what I'm going to want you to do is come back and just have another look at that word provisional in there and make sure that you understand why I didn't just say new knowledge and I said new provisional knowledge. There's always that element of doubt, uncertainty, provisionality of knowledge in science. We'll come back to that later. But for now, just notice how research design plays such an important role in this whole process of research in physical geography and science generally, in all research, in all academic and scientific research. So research design is about how you go about finding something out. And the first point I want to make is that there are a lot of different ways of trying to find things out. There are lots of different approaches to getting solutions to problems, lots of different approaches to getting answers to questions. But the key point here for you is to realise that some ways of trying to find things out are better than other ways of trying to find things out. And some ways of trying to find things out, well, they might give you an answer, but it's not going to be a reliable answer. It's not going to be an answer that you can put any trust in, or it might give the wrong answer and you'd never know. Whereas other ways of finding things out are going to lead you to more reliable answers that you can trust and put some faith in. So we're going to begin by talking about these different ways of finding things out. You can see on the slide there some more headings down below. Those are the topics that we're going to come on to next, after we've talked about these different ways of finding things out. So what I'd like you to do at this stage is just pause the video in a minute, or pause it on this slide, and just have a go at this exercise. Now, the idea of this exercise is to demonstrate in a very simple, everyday kind of a way that there are different ways of finding things out. And those different approaches, first of all, different approaches might be more or less appropriate in different situations. An approach which is really good for dealing with a question about the timing of floods might be very different from the best approach for asking about the history of debris in the base of a glacier, for example. There are lots of different ways of approaching research. Different methods are best for different things. And I just want you to demonstrate that to yourself by trying this very simple kind of non-sciencey exercise. So down the left-hand side, you can see there are some questions there, and it's about finding out about your friend or a member of the family, wherever you are. Do this with whoever you have, whoever you have around. And we're just going to ask some very basic questions. And then for each question that you're asking, I want you to try at least 2 different methods of finding out the answer to the question. For each of the methods that you use for each of those questions, jot down the answer that you get. You can do it as a thought experiment if you don't do it as a real experiment. But if you've got a friend handy, then go and ask them these questions. Otherwise, imagine the answers that you get, or kind of ask yourself the questions. And write down the answers that you get using each method. And I bet you'll get different answers if you use different methods to get answers to these questions. And then for each of the answers that you get, bearing in mind the method that you used, just jot down whether you have a high, medium or low level of confidence in the answer that you were given in response to your question. So I'm going to suggest that you pause the video now and just work your way through those questions, and then come back when you've finished, and I'll talk you through some ideas about what I imagine you might have got. So pause the video, do the exercise. Okay, have you done that? Are you back? Okay, welcome back. So I wonder what you got. So what were the questions? What colour hair does your friend or family member have? How might you find that out? Well, you could just have a look at it, and you might have a Munsell soil colour chart, or a Pantone colour chart, or a Dulux paint colour chart, and say, oh yeah, well, it's brown that is, or oh, it's blonde that is. Okay. Now what if you did that, but you did it outside in natural light or inside in artificial light? Or what if you asked them? Try that. So the first method could be looking. You say, oh, they've got light brown hair. And then you ask them and they say, oh, I have blonde hair. Oh, yeah, well, let's go and stand out in real. What about if you didn't dye it? Then what would it be like? Well, maybe our question wasn't very good. Maybe it isn't just what colour hair have you got, it's what's your natural hair colour? And suddenly everything gets more difficult. But even keeping it simple, you look at their hair colour or you ask them for their answer to what their hair colour is. What answer might they say? And which are you going to have most confidence in? Let's move on. Try the other one, the worst habit. What's your friend's worst habit? Well, again, suppose you ask them, do you honestly think they're going to tell you their worst habit? And is their opinion of what's worst going to be the same as what your opinion would be? So asking them is probably not going to give you a very reliable answer. If you ask me, I'm not going to tell you my worst habit. So maybe you have a new approach here. Maybe say, right, we're going to set up cameras, we're going to have a team of observers, we're going to monitor this individual for 5 years and see what the most egregious thing that they do is over that time period. There would be ethical issues involved in that. I don't suggest that you do that project. But imagine you did. Do you think you'd get the same answer by watching this person for 5 years to the answer that you get if you ask them? No, obviously you wouldn't. You'd get different answers and you'd have different levels of confidence. And that can apply to anything. So the next one, just does the person study at Keele? Well, you ask them, they say yes, and you think, well, that's fair enough. But they might be lying. They might be the secret shopper. They might be a government inspector pretending to be a student, but they're not really. Or they might actually have been thrown out of Keele, but they're sneaking back into lectures or something. You just don't know. So asking them isn't very reliable. Well, what if you go and look at the Keele, if you're allowed to, I'm sure you're not allowed to, but suppose you go and look at the Keele database record of who's a student. Well, then you've got to check their identity. There are lots of different methods of finding out the answer. That's the point. I'm sure you came up with lots of your own. They're going to give you different answers potentially, and you're going to have different levels of confidence in those different answers. So when you move on from hair colour and bad habits, and you're starting to think about landslides, volcanoes, mass movements, glaciers, rivers, climate change, etc., for the questions that you're asking, you need to work out what's not just what method could you use to find out the answer, but what's the best method to use for finding out the answer to your particular question, and have you set up your particular question precisely enough to enable you to get a sensible answer anyway. So that hair colour one, do you want natural hair colour, daylight hair colour under orange street lights? Be very specific about the question that you're asking. Okay, so that was a little exercise just to think about different ways of finding things out and recognising that different methods are going to be appropriate in different situations and some are better than others. What I want to do now is move on and think about the next topics on our list. We'll tie them all together by the end of the session. But I want to think now, under the heading of research design, I want to think about logic. And I want to think about two particular types of logic, induction and deduction. So induction and deduction, or inductive and deductive, they're two types of logic or reasoning, because that's really what logic is. It's all about just reasoning, just figuring things out in a sensible way, where your premises relate soundly to your conclusions. You don't come up with some random answer that bears no relation at all to the evidence. It's kind of the common sense of research. Now, inductive reasoning is all about, I've got it jotted down here, so a definition for you here. Inductive reasoning is about making inferences from a body of non-conclusive data. What's that all about? What I mean by that is that you make a series of individual observations. I look at that juggling ball, I look at that globe, I look at that stone, I look at this, I look at that, I look at some more juggling balls and some more stones, and having looked at a whole number of different examples of the thing I'm interested in, from that wide set of separate observations, I draw together a general conclusion. Now let me give you a silly example just to illustrate how that can go wrong. Suppose I look at all the dissertations, the undergraduate dissertations that have been presented in the last 10 years, the last 30 years that I've been involved in marking, and I look at them all, and I look at all sorts of things about them, but I notice that the typeface that they're written in, and it turns out when I look at them that all the dissertations that have got first class marks, the typeface was Times New Roman. And I think, right, well, based on that observation then, all these dissertations, the ones that have got first class marks have Times New Roman. Well, in that case, that must be what you have to do to get a first class mark. I've seen this correlation. I'm going to infer from all those different observations of lots of different dissertations that must be a general rule. And I'm figuring out that general rule by seeing all the separate cases. Now, that's a silly example in a way, but it's a helpful example because it demonstrates straight away one of the problems of inductive reasoning. It isn't actually proof that that's the reason. That isn't the reason you don't get a first class mark. Even if you go and look at all the dissertations and they all have Times New Roman font, that isn't the reason they got first class marks. There'll be other reasons. So let's think about deductive reasoning. Deductive reasoning works the other way around. Instead of starting with lots of separate observations and trying to generate a rule, it starts with a rule. So using the dissertations example, it says, for example, we might say, well, I'm looking in the handbook about the dissertations, and it says that in order to get a first-class dissertation, you have to follow these rules. You have to have a good research design. You have to do this, you have to do that, you have to do the other, and so on and so forth. So that starting point is something from which I can then step out and say, okay, so from this general rule, I can now look at all the individual cases, and I can see that, yep, the reason that dissertation got a first class mark is because it did tie back to this rule. Well, that dissertation, well, obviously that didn't get a first class mark because, look, it didn't tie back to that rule. So there's a general proposition, if you like, looking at my definition here, whereas inductive reasoning was making inferences from non-conclusive data, deductive reasoning starts with a general proposition and from that works out specific conclusions for individual particular cases. So I've got my general rule, now I can say, yep, that's a juggling ball. No, that isn't a juggling ball. No, that's not a juggling ball, it's a globe. Although again, you can see that I haven't set up my question very well because you can just about. You get the idea. I could juggle with those globes. So what's your definition of a juggling ball? So there are all sorts of problems with research design, like we saw earlier. But the point here is that inductive reasoning, starting with lots of examples and drawing together a rule, is different from deductive reasoning, having your rule and then applying it or testing lots of different examples against that rule. Now, let's have another exercise that will help you to just see that a little bit more clearly. So I want you to think about these logical syllogisms. And a syllogism is just a kind of logical exercise. It's an argument or a statement, if you like, that has this particular structure. There are two premises or starting points that aren't up for question. That we're just saying, well, this is a fact and this is a fact, premise number one and premise number two. Given those two facts that we're not questioning, those are our givens, those are our assumptions, our starting points. But if those are true, well then here's a third thing, and I'm saying that that's also true because those are true. So I have a premise, I have another premise, and then I have a conclusion which I'm saying is follows from those premises. So here are some examples. Example A is a valid syllogism. This makes sense, this is logical. All cars have wheels. So every car you see, if we're calling it a car, then at the moment, for our current definition of car, all cars have wheels. And we're not questioning that, we're just saying that's true. If you want to say, oh, but space cars don't have wheels, I don't care. For this argument, our premise is unquestionable. All cars have wheels. Here's our second premise. Not only do all cars have wheels, but point two, Herbie is a car. Okay, so all cars have wheels, all things with this label are like that. Herbie is one of those things. Therefore, logically, it follows that Herbie has wheels, because Herbie's a car and all cars have wheels. Well, Herbie must have wheels then, because Herbie's a car and all cars have wheels. You see how that works? It's a logical correctness to it. But look at example B, which at first glance you might think makes sense, but let's go through it. All cars have wheels, okay, so that's our same rule. Herbie has wheels, okay, so Herbie has wheels. I'm saying, therefore, Herbie is a car. No, Herbie is actually a supermarket trolley. That has wheels as well. That isn't a logical connection. Example B, you can't arrive at the conclusion that Herbie is the category A thing in the first row. Herbie isn't a car just because he has wheels, because other things have wheels as well. Go back and look at example A, thinking, oh, that must have a fault as well. No, it doesn't. Example A is okay, because the way that we've set up our argument, all cars have wheels, Herbie's a car, yeah, so Herbie will have wheels, necessarily. It follows logically. The second one, all cars have wheels, Herbie has wheels, therefore Herbie's a car. No. Herbie could be something else that has wheels. We didn't say that other things don't have wheels as well. So you've got to be careful setting up your argument. Now you might be thinking, why on earth are we doing logical arguments? This is meant to be a physical geography lecture. The reason is that when you're saying, well, I measured round pebbles in the bottom of that stream, and round pebbles only come from streams, therefore those round pebbles haven't been put in there from somewhere else, they were created in that stream bed. Well, that's the logical argument, that's the kind of logical structure you're using. Look, I have a rock here that has faceted, sub-rounded morphology, and there are even kind of striations on there. Well, if the only mechanism that can create that morphology is glaciers, and this rock has that morphology, this must be a glacial erratic. And that's the kind of logic that you see geographers using all the time. Oh look, this happened and that happened, therefore this must be the reason for climate change. Well look, this rock has that shape and this weight, therefore it must be this rock and it must have been affected by fluvial or glacial or whatever action. So all we're doing with these syllogisms is saying, look, this is what physical geographers do all the time. Are they getting it right? And that's what you need to be able to be in a position to judge. Partly for your own work, when you're doing your own research in your dissertation or whatever, but partly also for when you're judging the work of other physical geographers, when you're judging my work in the later part of this lecture, for example. So moving on, here are some examples for you to work on. And I'll come back to these in a follow-up video. Actually, I think later on. We'll come back to this at some point. Maybe in the live session at the end of the week. But here are 3 syllogisms for you to have a go at, and I just want you to identify whether the logic of these syllogisms is valid or not valid. All idiots are happy. All geographers are idiots. Therefore, all geographers are happy. Some geographers are stupid. No one who is stupid is wise. Therefore, some geographers are not wise. Some pearls are not silver. All silver things are beautiful. Therefore, some silver things are not pearls. What's all this rubbish? Well, these are the kinds of arguments that you will find in geographical research. All of my stones were round. All glacial stones are round. Therefore, all glacial stones are my stones. Try it out, just see if you can do it, and we'll come back to this in the live session or in a follow-up video. But it's important that you train your brain to spot invalid, illogical reasoning. Now I think at this point, I think this is at the stage you can pause the video on that, or bring the video back to that and pause it and work through those. But I think this is probably a stage for you to have a little break, do those exercises, think it through. If you're doing this video all in one go, this might be a time to have a break, and then we'll carry on when you're ready. Nobody's made me a cup of tea, so I don't know if I get a break or not. Okay, have you had your break, or have some of you brave and foolish souls decided to soldier on without a break? Okay, let's get going. So we've talked about there being different ways of finding things out. We've talked about the importance of logic, and I mentioned induction and deduction. I want to move on now to a name that you need to be familiar with, Karl Popper. He's a philosopher of science, and he wrote a book called The Logic of Scientific Discovery. And a lot of present-day physical geographers, whether they know it or not, they follow in the footsteps of Karl Popper's logic of how we should and maybe shouldn't go about research. Not everybody likes his approach, and for the people who are about to shout at me saying, you can't push Popper on these poor students, there are other ways of doing science as well. Yes, of course, we said earlier, there are different ways of finding things out, and some approaches are more appropriate in some situations and others in other situations. But understanding what Popper says is a really good starting point for understanding other approaches as well. And in many physical geography situations, Karl Popper's approach, or the hypothesis testing approach, which kind of relates to what Popper was talking about, is very appropriate. When you read up on Popper, you might find people not always saying, oh, he was interested in hypothesis testing. You'll see that he was interested in something, or he talked a lot about the idea of critical rationalism as a scientific process, and the relationship between induction, which he didn't believe really worked, or didn't really happen, and deduction, which he says is the most valid way of doing science. So let's just have a little bit of a chat about Karl Popper, hypothesis testing, and whether we can falsify some of our ideas or accept them, or whatever. Let's see where we are with that. Now let's do it again by thinking about an example. So I'm going to talk about how we approach science by a hypothesis testing method, kind of based on the kinds of things that Karl Popper talked about. We'll talk about Popper more in second year, but for now let's just think about the hypothesis testing as a way of getting answers to questions. So for this exercise, simple question. If I had some soil, I'd give you a handful of soil and say, well, this soil is very, very red in colour. Why is this soil red? Simple question. Why is this like this? Why is this juggling ball one colour and that's another colour? Why is this tape only 30 metres long? Why did I paint that? You can say why is a great question. And if someone gives you an answer, just say, yeah, but why? You can't go wrong with why as a question. You're looking for an explanation. Now, when you ask a why question, or what causes this, why does this happen, lots of answers may well spring to your mind, but you don't know which is the right one. Why am I sitting here? Well, it might be because I sit here to do the lecture. It might be that I sit here because I've been locked out of the other room. It might be that I sit here because this is the most comfortable chair in the house. There are lots of reasons. I wonder which is the right one. Well, figuring out the right one from a number of possible answers, that's hypothesis testing. Each possible answer to your question, that's a hypothesis. So why are these soils red? Well, one answer might be that the red is caused by iron in the soil. That sounds like a sensible suggestion. Rust goes red, doesn't it? So maybe iron in soil. Maybe it's the red soils is because of the iron in them. That's my proposal for an answer. That's my hypothesis. Okay, great start. We have a question. We have a hypothesis. Hopefully there'll be other hypotheses as well. It might be due to bacteria in the soil. It might be because somebody spilt red paint in the soil. It might be because whatever, all sorts of reasons. But let's just take one at a time. Hypothesis one, it's the iron. Now, from that hypothesis, predictions follow, or expectations follow. We say, well, if that was true, if it is because the red is caused by iron in the soil, well, what would I then expect to... So for each of those possible outcomes, I have to think, well, what would be my conclusion if that was the outcome? If there was iron in all the soil, or iron in all the red soil but not in the black soil, for each of those possible outcomes, what would I then infer? What would be the implication of that for my hypothesis that the redness is caused by the iron? Well, this is a very simple case, so we can say, well, if there's no correlation at all, if it turns out that the red soil sometimes has iron, sometimes doesn't, the black soil sometimes has iron, sometimes doesn't, well, that lack of correlation, that would be a falsification of my hypothesis, because my hypothesis implied that there should be a correlation. There isn't a correlation, therefore my hypothesis must be wrong. So I've confidently falsified that hypothesis, so I can kind of reject it. But suppose it was the other way around. Suppose I went out there and there was a correlation and all the red soils had iron in and all the black soils didn't have iron in. Does that mean that, oh, I've proved it, I've verified my hypothesis? No. This is where you have to be careful, because correlation does not imply causation. There might be something else which is causing both the iron and the red, for example. It isn't that the iron is causing the redness, it's that, well, like I said, maybe somebody spilt some paint into the soil and the paint has made the soil red, and maybe there was some iron content in the red paint. And so it isn't that the soil is red because of the iron, the soil is red because of the paint. So correlation doesn't necessarily prove your relationship, but the lack of a correlation can falsify your relationship. And this idea of falsification, that was at the heart of what Popper was arguing, that we should be going out there and trying to falsify our ideas, because we can do that confidently if they are wrong. There's no point going out there to verify our ideas, because finding some kind of correlation, well, it might be spurious, there might be some other thing which is causing it, not the thing that we're actually interested in. Now, Popper's specific example that people always use as an example of hypothesis testing was about the colour of swans. He was talking about whether swans are all white and what would happen if you found a black swan. So imagine that our next question is, well, what colour are swans? Are all swans white? And you could say, well, let's take this as a hypothesis. Let's do this by hypothesis testing. Let's say, hypothesis, yeah, all swans are white. Well, what's the test? What's the prediction then? Well, if all swans are white, then we shouldn't be able to find a black one, a blue one, a pink one or anything else, because they're all white, so there can't be any other colours. So what's our required observation? Go and look for colours of swan that aren't white. So what are the possible outcomes? Well, we might find only white ones. We might find white ones and other colours as well. We might find that there are only other colours. They're all black and blue and green and there are no white ones. But if we find, suppose, that all the swans we go out and look at are white, but we've only looked at 5 or 100 or 1,000, or I don't know how many swans there are in the world, but if we haven't looked at every single swan, then even if all the swans we see are white, can you absolutely confidently say that all swans are white, or only all the ones I've seen so far at the present day, not thinking about the future or the past, and not wondering if I've missed some in some far-flung part of the world? You're going to need to look at an awful lot of white swans before you can say, yes, they are all white. But what about if you found one black swan, just one? So you look up in the yellow pages, black swans please, and you discover they've got some at Chester Zoo, or you discover there's one on the lake in the village, and you say, right, let's go and have a look at that one. Yeah, seen it, one black swan, thank you very much. What does that one observation do for your hypothesis that all swans are white? It falsifies it, absolutely and confidently. Falsification is reliable and useful. Verification leaves you still wondering. So what do you do if you seem to be constantly verifying your hypothesis? You just keep finding white swans. Well, of course, if all swans really were white, you would indeed only ever find a white one. It's just that you can never be sure that you've got to the end of your searching. So if you keep finding verificatory evidence, you retain your hypothesis as provisional knowledge. And that's really what scientific knowledge is. It's all the hypotheses that we haven't managed to falsify, but we don't know if that's because they're actually the right answer, or if it's just that we haven't yet falsified them because we haven't looked at all the examples, or we haven't invented the right test, or whatever it might be. So scientific knowledge, and this is why I called it provisional early on, scientific knowledge is what we haven't yet managed to falsify, and we don't know whether maybe one day we will, or if we've actually stumbled on the right answer. Other than scientific knowledge based on falsification, because if we've falsified something, we can be logically more certain about it. That's the logic, anyway, behind Karl Popper's critical rationalism, and following through into hypothesis testing, which you will find is a very common approach in physical geography. So, research design by hypothesis testing. Falsification, you find a black swan, well then you can reject the hypothesis. If you fail to falsify because you only find white swans, well then you provisionally retain the hypothesis. It doesn't mean the hypothesis is true, it isn't verification. You need to carry on with more tests, and scientific knowledge is the as yet surviving hypotheses. So that's what hypothesis testing is all about, and you will be doing a lot more of that probably in your second year when you begin to think about how you're going to design your own dissertation research. Hypothesis testing may or may not be the appropriate best approach for you in your research. It depends what you're doing, and we'll talk about the choices that you make about what is the best approach. We'll talk about that later on as well. I'm going to draw to a close here, but I'll just show you the first slide, if you like, from what's going to be the next video in this series. We're going to take an example project, this research I did decades ago in Greenland. It's very old research. Well, it is groundbreaking research, but it's quite a long time ago. But it's a really nice example for you because it really pulls out in a very simple, straightforward way these ideas of hypothesis testing, hypotheses, predictions, tests, and so on. So we'll move on and we'll do that in the next video.